Hello everyone, I am Romain Carletto, PhD student at LIFAT laboratory in Tours University in France. The work I will present today has been supervised by Professor Cardot and Nicolas Ragot, also from LIFAT, and is funded by Centre Val de Loire region and by Madmix Digital, a creative studio specialized in web advertising and digital communication. This work aims at experimenting a baseline model for web advertising layout generation on suitable and challenging synthetic datasets. At Madmix, as at any other player of the layout industry, experienced designers and developers spend enormous amount of their time to arrange elements, which means to define the location and size of those elements within the frame containing the advertisement. It is a time-consuming job. It is done manually and it is very subjective, but in the end, an advertising that has been arranged by an experienced designer generates significantly more clicks than others. Finally, relationships between locations, sizes, and categories of the elements to be arranged are very specific in web advertisement layouts and differ significantly from other graphical document layouts. Earliest works on document layout generation use templates or low-level rules that can be combined by the user. Later works turn aesthetic criteria into sophisticated objective functions and then optimize these quantitative functions. But there were limitations. These methods are too reductive, and settling a hierarchy among the terms of the objective function remains problematic. Finally, most recent works leveraged deep learning methods possibilities. Learning methods have the advantage to model implicit rules from very simple objective functions. Among those learning methods, deep networks allow to reach levels of abstraction that are very useful in graphic creation. For example, these methods give very impressive results in image generation. Based on deep networks, deep generative networks have two advantages. They require no objective function, and they allow us to have control on the variability of the generated layouts. However, the state of the art actually went directly from classical methods without any learning to deep generative networks and very sophisticated generative networks. So we wanted to check what supervised deep networks can achieve in their own. When starting to experiment on web ad layouts, we faced a very important problem, which was the lack of data. First, the ownership of a web advertisement is shared between advertisers, broadcasters, creative agencies, and advertising studios. So to bring together thousands of web advertisements requires to get the agreement of as many different entities. As another issue, the same graphic information can be coded in an infinite number of different ways. For example, where is the upper left corner of an element can depend on many different parameters and can be coded in many different ways. So we just can't retrieve the information of where is an element or how big is an element from the code. We cannot get exact information about this. Of course, document layout datasets already exist and can be used to partially test or model, but they do not address our exact application problems. The most popular document layout dataset in recent years has been Ragot dataset, which contains app pages layouts. However, as an example, our layouts present large empty spaces while elements are juxtaposed to each other in Ragot and in articles layouts. As another example, misalignment is preferred on web ad layouts, while Ragot layouts used to be left or center aligned. And even if advertisement layout and other document layouts can have common element categories such as image and text, other element categories such as CTA and logo categories are very specific to web ad layouts, and they have a very high impact on locations and sizes of related elements in web ad layouts. Finally, there is no nested elements in advertising layouts, unlike Ragot and abstract scenes layouts, where these nested elements are found very often. Therefore, we created 3 datasets of our own. A fictitious synthetic dataset, a first synthetic dataset, has been created which contains 100,000 layouts created from fake layout rules that are arbitrarily difficult to learn but easy to evaluate since they are explicitly and quantitatively defined. We also created a second synthetic dataset, which is this time a realistic synthetic dataset. It contains also 100,000 layouts, but this time it was created from realistic layout rules, which are similar to some basic layout rules in the web advertising industry. And in this dataset, the categories of the elements are not arbitrary categories, but instead they are categories that you can find in real web ad layouts such as CTA, logo, and text and images. Finally, we created a small real dataset which contains 100 only of real layouts produced by Manix designers that we segmented ourselves. This dataset is used to assert that training and evaluating a model on our 2 synthetic datasets increases its performance on a real web ad layout dataset. Our first synthetic dataset contains several types of features. Geometric components such as location, sizes, and semantic asset categories. 2 sets of rules were used to create this dataset. General rules make sure that elements are not overlapping or exceeding the advert frame, and that minimum spaces are respected between elements. Within those constraints, the elements are laid out randomly. Specific and additional rules are then activated on specific combinations of assets. For example, if all elements are blue, then they all stick to the left border, as you can see on the right of the image. The specific rules take precedence over the general rules and concern only a few samples for each specific rule, to evaluate our model's ability to learn rules that impact only a fraction of the dataset, about 3% for each specific rule, against 60% of the layouts that are only concerned by the general rules. This also allows to evaluate with high precision the ability of our model to learn hard and deterministic rules that impact a minority of elements in a dataset where the majority of the elements are set partially randomly. Our model is a deep network with 15 layers activated by a relay function. We applied a variant of the residual block from ResNet. Within our version, only 1 layer per residual block. The residual block prevents the vanishing gradient issue, already limited thanks to the relay functions. It also allows us to better restrict the exploration of the feature space around the manifold that contains the most decisive combinations of features. You can see here some visual results on our first synthetic dataset. On the training layouts on the left, elements are laid out through additional rules in a deterministic way due to the specific combination of these categories. We can see on the generated layouts on the right that order, location, and size are very close to the expected ones, and that there are no overlapping elements except the ones that are supposed to be, as you can see in the layouts with red, green, blue element sequence. These elements are overlapping on the training samples, and here again they are overlapping on the generated samples. Quantitative evaluation is based on 2 different metrics. In the first metric, we measure the maximum error on each element features and average these maximums over all evaluated layouts. In the second metric, we simply consider layouts in non-compliance with general constraints, no overlap and no screen limits exceeding, as in critical errors, and thus count how many layouts are in critical errors. We see in the right part of table 1 that the results of our deep residual network on the first synthetic dataset match the industry requirements. There are nearly no overlap, and maximum deviation between expected and observed feature values are of a few pixels only. Similarly, our model performance reaches industry requirements on the second synthetic dataset. We first settled a reference training protocol, which consists in training our model on the real dataset, then evaluating our model on the real dataset again. As expected, this led to poor results, because there are too few layouts in the real dataset. We then experimented the protocol A, which consists in training our model on the second synthetic dataset, then evaluating our model on the real dataset. Finally, we experimented the protocol B, which consists in training our model on the second synthetic dataset, then training it again on the real dataset, and then evaluating it on the real dataset. The following results show that using our synthetic dataset allows significant performance gain on the real dataset. Finally, the following quantitative results show that our deep residual model reaches significantly better performances than a baseline 3 layers MLP model. Here are the visual results for the real dataset, which for each pair, the ground truth on the right and the layout generated by our model on the left. The results are visually satisfying. Sequential order of the elements is respected. Laid-out elements are neither overlapping nor exceeding screen limits. The balance between occupied and free spaces is very close to the ground truth. And finally, we also notice that the images and the text are larger than the logo on the CTR, which is something that is precisely expected by the designers in web advertising layouts. As a future lead, we will experiment on integrating background images information in foreground element layout process by applying CNN architectures on the background images. Usually, such models output saliency maps or bounding boxes corresponding to semantic categories. So we would like to generate bounding boxes of elements in balance with the background elements. As another research lead, we would like to start integrating simple animations, such as traveling or zooming animations, and progressively reach more and more sophisticated animated layout generations. Another interesting approach would be to compare layout generation models based on standard architectures with related models based on graph neural networks. The latter seem actually more adapted to a sequential approach, setting relations between elements in a first step, element by element, then generating bounding boxes from such generated graph in a second step. Also, graph neural networks have very interesting generalization capacities and could be more easy to turn into something that we can apply to other fields, such as image generation and video generation. So this is a very interesting axis of research. Similarly, evaluating benefits and costs of attribute-guided layout generation against unguided layout generation would be an interesting approach. By attribute-guided layout generation, we mean a layout generation where you can give as input some categories of elements, some labels, some images, but also some reserved areas, some constraints that users can just give to the AI, and therefore have an interaction between the users and the generating model. Finally, going beyond the bounding box modeling and generating pixel-wise advertising layouts could be a very challenging work, but that also could be a work of high interest and could actually have some interesting developments in layout generation, but also in image generation, maybe in video generation. So this will be definitely a future axis of research. I would now like to thank you for your attention, as well as the organizers and reviewers of our work. Finally, I would like to thank my supervisors, Professor Cardot and Nicolas Ragot, who have guided and supported my work so far. Thanks to everyone.